All right, so you've already done this in lab, but we're going to specifically talk about it for today. Gravimetric analysis. So what does this mean? Gravity meaning gravity, weight, and metric meaning measure. So we're weighing something. So our lesson objectives will define what quantitative analysis is. We'll define the process of gravimetric analysis. We'll revisit hydrates, and then we'll determine mass percent of water using gravimetric analysis. So what is quantitative analysis? A quantitative analysis answers the question, how much? This answer is normally given as a mass or a concentration, though sometimes it can also be a volume. Mass is usually taken using an analytical balance, because that's the most sensitive type of balance, and spectroscopy is often used to determine how much is in each solution. Quantitative analysis requires precise and careful work to get reliable results. This presentation will deal specifically with the quantitative technique of gravimetric analysis. So in other words, we're going to deal with that balance. As a side note, if you're wondering, this schematic here is for a UV-vis spectrometer, which you will get to use in lab later in the term. All right, so gravimetric analysis techniques were some of the first employed by chemists because of their simplicity. You can weigh your reactants and products to explore information about how much you have of a certain analyte. Analyte here is a fancy way of saying thing you're measuring. Literally, it's just the chemical species you're interested in. So the law of definite proportions was explored by doing experiments like this. So for example, you could burn pre-weighed methane and oxygen gas to make carbon dioxide and water in a closed system. Also, I do not recommend heating a closed system. It could explode. Anyway, you weigh the products and show that the mass is conserved, or you could show that you use the same proportions and you always come out with the same proportion of products, which is what a lot of scientists systematically did to demonstrate the law of definite proportions. Like they weighed stuff out, put it into sealed containers, reacted it, weighed it again. You get the idea. Lots of these types of experiments were used to show the law of definite proportions. This type of analysis is a powerful, inexpensive, relatively speaking, and therefore still relevant tool for chemists today. So let's revisit the topic of hydrates. Hydrates are a solid form of an ionic compound that has water in the unit cell. In the image on the right, we've got a unit cell of copper sulfate outlined with the dashed lines, and you can see that there are red balls with two white balls attached. Those are connected to orange balls. These red and white balls are water molecules that make copper sulfate a hydrate, copper being the orange. We've covered the nomenclature of hydrates, and we know that we can name the ionic compound like we normally would, and then add the number of water by using a prefix and the word hydrate to indicate that you're dealing with water in the crystal. So how does that relate to gravimetric analysis? I'm glad you asked. If you heat the hydrate crystals, you can evaporate the water from the solid. What? So that means you can weigh a sample before and after heating to measure the amount of water in our hydrates. So let's do a little flow chart. When we use gravimetric analysis in hydrates, our goal is to evaporate all the water and calculate the mass percent of water in the sample. So we weigh a container. We put a hydrate crystal in the container. You heat that sample, either with a Bunsen burner or an oven or some other heating technique. Heck, you could use the sun. Then you weigh the dry sample. You repeat the heat and mass steps to make sure that all of the water has indeed evaporated, because maybe you weren't done yet. But if you heat it again and you weigh it again and it weighs the same amount, you were actually finished. This is a pretty simple process. None of that is hard. Weighing things, heating them, weighing them again, not difficult. So how do we use this powerful and simple technique? Let's calculate the mass percent of a hydrate from a fictitious data set. Meaning, I made this up. All right, so we want to know what our mass percent of water is. And anytime we do a mass percent, it's mass of the thing you're interested in. So in this case, water over total mass times 100. Simple enough. So how do we find each of those components? Well, we're going to start by identifying how to get the mass of water out of the sample. Well, we have in this table here an empty crucible, a crucible plus hydrate, crucible plus dry sample 1, crucible plus dry sample 2. Why am I saying dry sample? Well, I heated it. So we're hoping that the water evaporated fully. So the numbers here for the dry samples are really close. The only variation is within that last digit. So we know that this is, in fact, a dry sample for reals. So how do we find out how much water we lost? We're going to use subtraction. Okay, so we've got crucible and dry sample, right? And if we take away the mass of the crucible, we would get the weight of the dry sample. Is that what we want? No, we want the mass of the water. If we take the crucible plus the dry sample and we subtract it from the hydrate, we'll just get the water. So here we go. 12.2108 minus 11.8527. And both of these numbers are grams. Don't want to forget that. When we do subtraction, what is the sig fig rule? That's right. It is the least precise number of place. So in both of these samples, you go out to the fourth past the decimal. So that is our place value that we're going to. So we take 12.2108 and we subtract 11.8527. Why 8527 and not 8528? Well, we always want to go with the lowest one. Maximum amount of water evaporated. All right, and we get 0.3581 grams of water that evaporated. All right, now we got the water. How do we find the mass of the total? What's that crucible got going on? We're going to take this one and subtract that one, right? So 12.2108 grams, that's where we start again, minus, in this case, 11.2979 grams. And again, our sig fig rule for addition and subtraction says that we're going out to the fourth past the decimal. So when we do 12.2108 minus 11.2979, we get 0.9129. We'll pretend that that 9 does not look like a G. Okay, so we put in the end our 0.3581 grams of water over 0.9129 grams total times 100. All right, so what do we get when we do that? 0.3581 divided by 0.9129 times 100 gives us 39.23. All right, so now why did I do 4 sig figs? Because when we're doing multiplication or division, the number of sig figs is determined by the lowest number of sig figs in the incoming information. And in this case, both of them have 4 sig figs, so we should have 4 sig figs on our answer. All right, so this wasn't terribly hard. But let's say we want to extend from there. Let's say we want to calculate the moles from the mass percent. So we want to determine the waters of hydration on cobalt chloride NH2O if the compound is 45.6% water. So what does waters of hydration refer to? It's how many water molecules are in the unit cell of the compound. It may also be referred to as a water of crystallization. Anyway, we need to determine the number of moles of water per cobalt-2 chloride formula unit. So we start by assuming that we have 100 grams of this hydrate in total. Why? Because we're lazy, and that's easy. Okay, so we have then 45.6 grams of water, and then 100 minus 45.6 gives us 54.4 grams of cobalt chloride. That is a terrible CO. Let's try again. COCl2. Okay, so now we have the mass of each one of these components, but our balanced chemical formula is in moles. So we're going to take this 45.6 grams of water, and we're going to divide by the molar mass, so 18 grams per mole. Okay, and when we do that, we get 2.53 moles. All right, then over here, we're going to take our 54.4 grams of cobalt chloride, and we're going to divide by its molar mass of 129.8 grams per mole. And when we do that, we get 0.419 moles of cobalt chloride. And specifically, this is cobalt-2 chloride. I'm being a little bit lazy here, but I'm going to state that now. Okay, so we're in the home stretch here. When we get to the point where we have our stuff in moles, we're going to divide by the smallest number of moles so that we can get to a whole number. So in this case, that is the 0.419, and this will give us a whole number. And we're going to round it. So this is about 6. And over here, if we divide by 0.419, we get 1. And number divided by itself is 1. So in the end, we have COCl2, and there's 1 of them, for every 6 H2O. Not so bad. We can do this thing. All right, to summarize, quantitative analysis answers the question, how much? Gravimetric analysis is a form of quantitative analysis where you weigh things to determine how much. And finally, you can determine the chemical formula of a hydrate using gravimetric analysis by first determining the mass percent of water by heating the sample, because you evaporate the water. Then you assume 100 grams. You convert each component to moles. You divide by the smallest number of moles to get whole numbers, and then you write your formula based on those whole numbers. So all in all, this is not super complicated, but it does require that you pay attention to details.